Hi everyone. We have a good question from the chapter of electrostats. It's not just a question on electrostats, it's also a question on work, power, and energy. Okay, so let's quickly go through the question. We have got a rod of length L and it is uniformly charged with a linear charge density lambda, and it's kept on a smooth horizontal surface. It's smooth, okay? And the right end of the rod is in contact with a vertical fixed wall. A block of mass m and charge q is approaching this particular rod with a velocity of v from a point which is very far away from the rod. We have to find the distance of closest approach between the block and the left end A of the rod. Now, let's just try to visualize what's happening here. So this thing is, this small block over here is coming from a point which is, at an infinite distance away from this rod. Okay, it is slowly approaching, not slowly, sorry, with a velocity of v. It's approaching, or rather it was projected with a velocity v. Okay, and as we know that both of them have positive charge, right? And positive charges repel each other, so do negative charges. And as these two bodies repel, uh, the speed of this small block, it goes on reducing at a point till the point it becomes zero. Okay, so that is the distance of closest approach. Now this is the concept which we will be using, and we use the law of conservation of mechanical energy to solve these kinds of questions, right? It's very obvious. So yeah, what is mechanical energy? It's equal to u plus k, right? U is kinetic, I'm sorry, U is potential energy and K is kinetic energy, right? So let's just find the value of U at, say, a distance x, when it's a distance x away. Like, let me show you in this diagram. Okay, so let the distance of closest approach be equal to A. Okay, this is the closest distance which these two bodies will be able to get to. Okay, let this distance be x. We need to find the potential energy, right? So let's start by finding that. Finding the potential energy between these two bodies. This is A, this length is L, and we have a small point, or not a point, sorry. We've taken a small strip in the rod at a length x away from this small block. Okay, and the length of this small strip is dx. Okay, so yeah, let's find the potential energy between the block and this small strip, and then we will integrate that to find the total potential energy between the rod and the small block. Okay, so du will be equal to 1 by 4 pi epsilon naught into q. Q is the charge on the small block. The charge on the big rod, or rather in the small strip of that rod, will be lambda dx, and this will be divided by x. This is the formula for potential energy, right? Now we basically integrate this on both sides, and I will put the limits afterwards. Okay, so this is 1 by 4 pi epsilon naught into q lambda ln x, and the limits are from a to a plus l. Why? If you see, the smallest distance between this block and this rod is a, and the maximum distance is a plus l. So that is what my limits are going to be, and this will be from 0 to u at the upper end. Okay, so this u will become equal to 1 by 4 pi epsilon naught q lambda ln 1 plus l by a. Okay, now we apply the law of conservation of mechanical energy. Initially, the value of potential energy, or the value of kinetic energy, is half mv square, right? The potential energy initially is 0, because that is what we consider the potential energy of a system when the distance between the two of them is infinity to b. All right, we consider that to be 0. This will be equal to Q lambda ln 1 plus L by A is the potential energy, and at the distance, the minimum distance, the kinetic energy will be 0. Okay. So upon simplifying this, we will see that 1 plus L by A is equal to e to the power 2 pi epsilon naught 2 pi epsilon naught mv square divided by q lambda. Okay, I'm sorry, I missed out on the 4 pi epsilon naught here. Okay, so this is what we will get, and from here we can easily find the value of A. All right, this is the value which we need. All right, thank you.